I will now be describing the relation between the project structure, the associated files, the initialization specific to PIC microcontroller, its relation to the actual circuitry and the schematic and the PCB layout, in order to get a better picture of how the program is executed and how different components interact. First, we will start with the program structure. So, as described in the code flow, the program has been split into different parts. So, the main code has all the initializations and all other program files. For example, the UART interrupts, the IMU interrupt, the IMU read function, other miscellaneous functions, the control function, encoder reading, have been included inside the main code. In order to avoid adding those files in the project separately, apart from that, the main code also has the oscillator configuration, the watchdog disabling, and the initializations which are required for various peripherals. After all the initializations are done, the main function goes into an infinite wait state, where it keeps waiting for various interrupts to occur. For example, the IMU interrupt occurs because of the change notification interrupt on any pin of the PIC microcontroller, and this occurs at 816 Hz as described in code flow. Out of the 816 interrupts, 7 interrupts are ignored, which means the frequency is divided by 8, and once in every 8 interrupts, the IMU is read, the encoders are read, the velocities are calculated, the x, y, theta are calculated using dead reckoning, the battery voltages are measured, and then the pitch angle is calculated in the control code. All the filters are run in a for loop. The pitch angle is calculated using a complementary filter, and then whatever the desired control law has been designed is calculated, from which the two torques, which are denoted as control 1 and control 2, are obtained, which are the left and right wheel torques. Then both the control torques are converted into voltage. The procedure will be described later, and this voltage is in terms of PWM counts, which can be directly loaded onto the duty cycle registers represented by P1 DC1 and P1 DC2 after the voltages are saturated, in order to avoid excess voltage being applied, which is also not possible, and it's a logical error. Hence the voltages are saturated to the peak value. It's the maximum duty cycle of the register, and it's loaded into the duty cycle register. And after the control is executed. The states are stored in an array. And it returns back to the IMU interrupt. Now a separate frequency can be chosen for transmission of the states to a computer or another robot. So that has been done at 50 Hz as described in the code flow. And the transmission is initiated by storing the first state into the transmit register, which starts off the transmission, and once the first transmission is completed, automatically the UART interrupt occurs, especially the UART transmit interrupt. And now this becomes an automatic process, even though some other program may be running, for example either an IMU read or control for the next instance. Once a UART transmit interrupt occurs, until the total number of states are transmitted, the flag is cleared and all other states are transmitted continuously. So after the next state is loaded into the transmit register, it goes back to whatever the code that was currently under execution or goes into a wait state. And if there are some data received using the UART receive, there is a UART receive interrupt which occurs, and since sense has to be made on what the received data is, whatever your desired data identification code has to be inserted here. After all these functions, the system returns back to the main program to wait inside this while loop. And this is consistent with the code flow described previously. Now we will see what are the features being used and what are the features which are actually initialized in the main program, and we will describe the corresponding features one by one. So before going to that, we will describe the schematic of the system through which all the features will be revealed. So this is the DSPIC microcontroller which has been used in the MIP robot. As it can be seen, many of the pins have multiple purposes. Hence these are called as remappable pins. There are many peripherals which can be internally multiplexed to be connected to the same pin. For example, if we take pin number 4, it has a option of program data, analog input 2, counter 2 input negative, remappable pin 0, identified as remappable pin 0, change notification interrupt number 4, or a generic port pin, port B, 0th pin. So depending on the internal configuration register, this can serve as any of these purposes. Hence there are plenty of registers which needs to be initialized in the main program so that the correct peripheral has been connected to this pin for proper functionality. And this can further be used as an advantage in circuit design itself, because the same peripheral could be connected to different pins of the microcontroller. It becomes advantageous to route a particular peripheral in a particular direction of the board, rather than forcing all of them to go in or go on one side. For example, in this circuit, the UART are going from pins 17 and 18, as can be seen here, the blue lines which are going here, the TX and RX, so which are both remappable pins, RP8 and RP9. Which has resulted in the signal not going all the way around from the other side of the microcontroller. So depending on optimizing the length of travel or to avoid the jump of layers of the PCB, some amount of flexibility exists because of mapping internal peripherals of the DS PIC to various remappable pins. Now this circuit has, as described from the hardware, it has two Maxon motor drivers to which two pins go from the microcontroller to each driver. So one is the PWM1 direction, whether it's clockwise or anti-clockwise, and then the PWM1 actual PWM signal, and the PWM2 direction, clockwise or anti-clockwise, and the PWM2 signal. So these are the only signals going from the microcontroller to the motor driver, and the motor driver works on 24 volts, which is the bigger battery. Next, here we have all the regulators. So the bigger battery is connected to the 24 volts, which is represented by VDD, as shown here. 24 volts is connected to VDD. So the 8.4 volt battery or the 7.2 volt with the peak volt 8.4 is connected to the 5 volt regulator, whose output is connected to the 3.3 volt regulator. There are a lot of test pins provided once all the circuits are in place in order to test the functionality, as shown in the circuit here, 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 etc. There is an option for the encoder jumper, as shown here. This is the connectors. This is the additional circuit board shown in the corner of this board, which is the small PCB which is used to connect the inertial measurement unit as described in the hardware, and has the small miniature connector which goes directly into the inertial measurement unit. There are buffers which convert the 5 volt encoder signals into 3.3 volt, which are the safety levels provided mentioned for the DSPIC microcontroller. There is one more SPI expansion, a 3-pin SPI expansion from the 3.3 volt DSPIC microcontroller to some external peripheral through this jumper JP1, which operates at 1.8 volt, which is shown here in the circuit board. If in case an additional board needs to be mounted on MIP in order to do some tasks using vision or for some further advanced processing, this port can be used to access all the states calculated in the PIC microcontroller and do the processing on the secondary board, and then return back the PWM values to the PIC microcontroller in order to be applied to the drivers. Then there are the protection circuits for the battery voltage measurement and the Zigbee module interface using the UART peripheral. As can be seen from the board overlay, so this is the board with all the components integrated. The small corner portion has been cut off in order to connect it to the inertial measurement unit. So these are the two switches which are used to control the MIP. This switch is used to deliver power to all the processing circuitry, and this switch is a soft disable enable pin for the driver to avoid disconnecting the battery very often. This is used in order to disable the drivers and apply zero voltage across the motors as shown here. So these are the actual schematic and the board and the actual soldered complete assembled board. Now we will describe each and individual peripheral, initialization, and what their functionalities using the code. So overall, this is the project structure. So we will open the code one by one and describe what's happening in it. So the main code has all the other C codes included in it and has the header files of the PIC microcontroller and the variables, user defined variables included in it, and for math functions, math.h. The oscillator has a preprocessor directive required, which is supposed to be programmed into a special region in flash, and this is a directive mentioned specifically for the MP lab software. And this directive says oscillator, internal oscillator, fast RC oscillator on, clock switching is off, and the fail-safe clock monitor is disabled, and the primary oscillator mode is disabled, which is dependent on a addition of an external crystal which we have not used. Yeah. We have used the internal PLL in order to convert the RC frequency, which is 7.37 megahertz, into 40 megahertz. Hence the PLL has been enabled, the watchdog is disabled, the code protection has been turned off for simplicity of programming, the power up timer is turned off. Next. since we are using only 2 pins as analog pins, please refer to the logic of each register in the corresponding PIC data sheet. So this corresponds to ADC port configuration register. As you can be seen, only the last 2 bits are 0, which makes them ADC pins for 2 batteries. Rest all are digital pins. So it's always important to have the correct configuration. Otherwise, for example, in the schematic, these 3 pins 4, 5, 6, which represents analog pins, actually go to a SPI clock, master in slave out and master out slave in. But if indeed it's an analog port, then the SPI module, the external peripheral, will not be able to interact with the PIC microcontroller. Hence it's important to have the correct configuration. Next, the PLL setup configuration has been shown. So this is a PLL multiplier. So there are 3 multipliers, post multipliers, and a PLL loop multiplication. So a total of 39.6, around 40 megahertz has been generated, which is the peak operating frequency of this DSPIC microcontroller. So after the PLL is enabled, in order for the clock to be stable, so the system has to wait for the PLL to get locked, which means it takes some time for the PLL output to become 40 megahertz and to be stable. Next, the stress registers represent the direction. 0 represents output, 1 represents input, and depending on the pin functionality, the corresponding directionality has to be set. The RPINRs represent remappable peripheral input register. For example, if we take the UART RX, UART RX is an input pin of the UART peripheral. Hence, the RX will fall under an input register remapping. On the opposite side, remapping peripheral output register. There could be many registers, and since the UART transmit is an output function, it falls under a remappable peripheral output register. So each one of these registers can connect a given peripheral pin to a desired pin of the microcontroller. So this TX pin of when I say pin, I'm saying the TX signal of the UART peripheral, which is generated internally, is connected to this pin RP9, which is a physical pin of the PIC microcontroller, using a multiplexer. There are many input remappable registers and there are many output remappable registers. Please refer to the PIC datasheet for a total list and which register is specifically used for mapping which peripheral and which pin to which pin. Next, we are setting up the PWM. Since this is a two-wheel robot, we are using two PWMs. So it is important to know which PWM influences which motor, and depending on the polarity of the connection, it's important to know what direction value is forward. There are many configuration registers in this. Main things would be generation of the actual PWM frequency, finding out what the resolution will be, and then mentioning the modes. For example, there are up counting mode, down counting mode, both up and down counting mode. Please refer to the datasheet of PWM, which we will describe later as a functional block, not specifically each register. As a functionality, we will describe how the PWM module works. For further details, please refer to PWM datasheet of PIC microcontroller, the corresponding PIC microcontroller. Next, the encoders are set up. So the encoder square waves can contain noise, hence digital filters are enabled, and there is a counter register internally, which is a 16-bit counter register, and the counter automatically counts up for clockwise or anti-clockwise and counts down for the opposite direction. Next, we see the UART setup. So UART setup has importantly three things. One is the baud rate generator, which contains a division of the processor frequency, and the division of processor frequency also has a pre-scaling which may be there in the U1 mode register. Apart from that, the U1 mode contains a polarity to be set for the receive pin and a polarity to be set for the transmit pin. Next, all the interrupts are configured and enabled. The chain notification interrupt, the first interrupt, represents the interrupt from the inertial measurement unit. We will refer back to the schematic. The CN0 as seen here, CN0 as seen here is connected to DIO1. DIO1 of the inertial measurement unit. In the actual board, it goes through a jumper through a cable to the inertial measurement unit. So this DIO1 is a pin in the inertial measurement unit which provides a pulse to represent to the PIC microcontroller that the data is ready. Hence the chain notification interrupt is used as an interrupt from IMU, and its priority has been set to the highest to prevent any missing of data. Next, the priority of the UART receive and UART transmits are set. UART transmit can be given the lowest priority. Then the interrupts are enabled. Please refer to the PIC datasheets to know which interrupt priority control and which interrupt enable control registers contain the bits corresponding to the desired peripherals. Next, the ADC is initialized. The ADC initialization has importantly the sample time for sample and hold circuit. The longer the time, the better the conversion will be after the sample and hold phenomenon. And there is an option to sample more than one channel one after the other without user intervention, and all these features are there in all these control registers AD, CON 1, 2 and 3. Next, the serial peripheral interface is initialized. It has been initialized as master mode, which means the PIC is the master and the IMU is the slave. So this SPI 1 is used for the inertial measurement unit, and the SPI CON 1 has all options for the ideal clock specification, pre-scaling, the actual clock frequency selection. The IMU data can be obtained from the IMU datasheet, which has been mentioned here in comments for ease of access. The SPI 2, which was shown here to connect an additional board, has just been initialized. The usage depends on the extra board and the corresponding study has to be done. Next, the IMU is initialized in order to generate the interrupts. So the SPI 1 buffer is a register into which the data is loaded, where the first byte represents the address inside the IMU and the second byte represents the data that needs to be stored. And in SPI, as the 16 bits are shifted into the IMU also shifts out some 16 bits, which has to be read back. So this flag SPI RF becomes 1 when it has received all the 16 bits from the IMU as well. Both happen simultaneously. So all these data specify that the DIO1 is supposed to generate the interrupts. Next, what is the rate at which the IMU is supposed to generate the interrupt, and then if necessary changing the sensitivity of the gyros and accelerometers. This now represents the full scale data to be mapped to plus minus 500 degrees per second. Some system parameters are calculated depending on the control law requirements, and then the main program goes into a wait mode. Now, since all interrupts are enabled, the first interrupt to occur will be the IMU. So we will now study the IMU. So this is the IMU interrupt function, which is the change notification interrupt. So once the IMU interrupt occurs, which currently it occurs at 816 Hz, the IMU flag is cleared. So there is a count being used to actually neglect 7 interrupts, and every 8th interrupt the IMU is read, the encoders are read, the battery voltages are read, states are calculated, control is calculated, the PWM is set, the count is made 0. Using an independent count, data transmission is initiated at a different rate. We will discuss this later. First, we will describe these functions: IMU read, encoder read, battery DC and control. The IMU read is a user defined function and it's not an interrupt. Hence, when this function is running, there could be other interrupts occurring. For example, if UART transmission is happening, then the UART transmission interrupt will be invoked. And for example, if the code is at this location, then the current location value pointer will be stored into the stack, and some useful registers will be stored into the stack, and the program will branch to the desired interrupt routine. So here we can see that the address of each particular data is given, and since we are reading, there is there is no data written into the IMU, and cyclically all data is read. So this flag is checked whether the complete data has been transferred from the IMU into the system. The IMU has a 14-bit data, which means we use a sign extension logic to extend the sign of the 14th bit into 15th and 16th bit. And the IMU has a specification of a minimum time required between successive transmissions. Next, all data are read in a similar fashion. So this is the address of the next data to be transmitted, which is the X gyro omega bx, and this is the address of the next data, and so on. All 9 IMU data are obtained, and they are stored in an array and exited. And the exit goes back to this location. Now the encoder read is called. Here the pos CNT represents the encoder counter register inside the PIC microcontroller, which is read. A successive difference is calculated between the current value and the previous value. An anti-backlash filter is run, and then a curve is fitted on 4 successive obtained data. The fit curve is then differentiated in order to obtain the actual velocity of the wheel. To avoid any spikes due to backlash, the same process is repeated for the left wheel. After the velocities are calculated, they are run through a linear filter, and 2 banks of filter are used. So the same velocity is passed through both banks. So the output of the first bank is used for dead reckoning, which is for further integration and calculation of x, y, theta. And the second bank output is used for the states, where the velocities are by themselves the states. Next, the dead reckoning is nothing but the integration of the third order. This is one of the equations, and these are the other 2 equations, which represents the kinematics of the 2 wheels of the mobile inverted pendulum robot. So for a first few seconds, the dead reckoning is not run. So in order for the filter output to stabilize, to avoid false data calculation because of overshoot of filters, and then dead reckoning is performed, continuously. And then again the control is transferred back to this point where the ADC function is executed. This ADC function, since it's a minor feature, it has been written inside the miscellaneous code. The miscellaneous code also has user defined functions for signum, user defined delays for a millisecond and for microsecond, and then the ADC function. In the ADC function, both the battery voltages are read and then return back to this point, control. Now the control code is called. In the control code, all IMU data are filtered using a linear filter, and the counts of the Y gyro, which represents the pitch velocity, is converted into radians per second. The conversion factor can be referred to from the IMU datasheet. A complementary filter is used to calculate the pitch angle. Next, as described before, what the desired whatever control law has been designed by the user is executed here. Here the control 1 and control 2 are the torques of the left and right wheel respectively. Next, the voltage is the torques are converted into voltage by using the model of the brush DC motor. This is a representative of the back EMF, and this is a representative of the scaling of the current, where current and torque are analogous for the brush DC motor. Next, the count is saturated to a max value because a value greater than this is invalid as a duty cycle. This represents 90% duty cycle. The Maxon motor driver are configured such that a 90% duty cycle input corresponds to 100% voltage. A 10% duty cycle corresponds to 0 voltage, and with the change of the direction sign, which was shown in the schematic, the change of the direction sign, again the same logic holds. With 10% duty cycle, 0 voltage is applied, and with 90% duty cycle, 100% voltage is applied. In case the MIP falls down, which is the check which has been done here, then a flag is set and the duty cycles are made 0, and this flag, when the next time the IMU function is run, will make sure that the voltages are not applied to the motor. Which means if the pitch angle exceeds some desired value, the motors are switched off. All the calculated states are stored in an array, and then the code branches back to the IMU interrupt routine to this point. The count is reset and the IMU interrupt exits back to the main code to the idle state. Now, if in case the count was such that the transmission is to be enabled, the first state is written into the transmit register, there is a 2-level buffer, hence 2 8-bit numbers can be stored successively. We transmit these states as 16-bit integers, and we scale it such that within 16 bits all data can be represented within the range, a desired range. So one complete integer is transmitted, which sets off the transmission. After the transmission occurs, a UART interrupt is generated. This is the UART transmit interrupt. So here up to 12 states are being transmitted. So after the first 2 transmissions get completed, the transmit interrupt is generated. This interrupt routine is called, and the code branches either from the idle mode from the main program, or some other code could be running and it branches from there and it comes here, and if all 12 have not been transmitted, then it stores the next state value into the 2 registers. There are 2 successive registers. There is an automatic shift register. Storing 2 values successfully causes a shift even though the same register name has been mentioned. Again, the code goes back to either idle or whatever other code has been executed. After the second state is transmitted, again the interrupt occurs. Again it comes back here. Again the third one is loaded, and so on. So after all 12 is transmitted, no further states are loaded, hence no more transmission interrupts will occur. And during any execution, if indeed the PIC microcontroller receives data from some other device like a computer, then the UART receive interrupt occurs. No code is currently been shown here, but in case the data which is received has a particular interpretation, depending on the interpretation, a code has to be inserted here. After the code is executed, the interrupt routine is exited and it goes back to whatever, either an idle state in the main code, or it goes back to whatever other code has been executed, was currently under execution before jumping to this routine. So this is the overall flow of the code as was described in the code flow as well. Now we can see that all the desired files are there. So this is a project, and once all the files are there and all the user defined variables are there, where shorthand notations are defined for pins, and all user defined variables are there, floating point numbers, integers, and all other gains and system parameters, and prototyping for the user defined functions. Now we use the build all function to build the whole code. As can be seen in the output window, that the build is successful. If there are no syntax mistakes in the program, there could still be a logical error, which is up to the user to mitigate. This output block also shows some features like how much data memory or the RAM is used, and how much program memory, which is the flash, is used. there may be some warnings, and if the PIC kit 3 programmer is connected, it will show us status. So this is the procedure to open the project, modularize the code for ease of debugging, and then build the project. And later we will demonstrate the programming through the hardware.